Hello everyone, let's play a game. I ask questions, you answer. So let's start with Pokemon. The most famous of them is obviously Pikachu. And what color is the tip of his tail? Surely you remember the black stripe, but it turns out it was never there. The tail is completely yellow, even in this generic one. Moving on to Monopoly, surely everyone has played it and you remember its mascot, a man in a top hat and mustache. So does he have a monocle? It seems like the image obliges, but it turns out that since 1936, in no version of the game does Mr. Monopoly have a monocle. Let's move on to the Volkswagen logo, two merged letters V and W. Now strain your mental powers. Is there a dividing line between them or not? The correct answer is yes, and it has always been there since 1937. Well, and the fourth question, how many states are in the USA? 51, 52. It turns out exactly 50, and there have never been more. Write in the comments how many questions you answered correctly. I'm sure most people answer everything incorrectly. I myself, when I was selecting them, got everything wrong, so don't worry, I'm with you. These are all vivid examples of the Mandela Effect, an amazing phenomenon where many people experience the same false memories. The most convincing explanation is quite boring. We often retell each other inaccuracies, confuse facts, remember parodies. So it's all psychology, cultural studies, and so on. But there's also a less popular but much bolder hypothesis that such mass memory distortions, well, you could say perception failures, have a physical nature. What if what we call reality isn't actually it, and we can only perceive some projection, some shell, while the true nature of things remains hidden from us? In that case, such false memories could be a failure in the construction of this reality, a bug in its structure that we haven't yet been able to discover. On one hand, it sounds crazy, some kind of Matrix game, and I'm Morpheus on a budget. But on the other hand, do we really understand how elementary particles, space-time, fundamental forces are structured? Yes, we have the theory of relativity, we have quantum physics, but they don't give a complete description of reality and a unified picture of the world. So there's some deeper explanation of how the universe is structured, and it's just madness, but it turns out, if we consider the universe a hologram, it seems it can be found. Scientists have long been seriously discussing the idea that our three-dimensional reality is an illusion, and we are all actually two-dimensional beings on some plane. But the third dimension doesn't exist, it appears, is completed on a microscopic level. Moreover, the same can be true of time. In reality, it doesn't exist, and it's only a consequence of some deep natural processes. All this is a manifestation of the so-called holographic principle, which scientists are using more and more often. And does it really follow that we live in a hologram and reality looks different? What awaits us in this episode? This could blow your mind. Therefore, to understand everything, we'll have to drastically change our worldview. Well, you could say reprogram our consciousness to a higher version. And since that's the case, here are three discs with which we'll do it. The holographic principle originates from the 90s. So the carrier is like this. The blue disk will clear the cache, perform defragmentation of knowledge, prepare the RAM, and will figure out how to record a whole 3 dimensions in 2, and how close physics is to creating a theory of everything. The red disk will install the main update package and drivers for a new understanding of reality. You'll learn about the mysterious add SCFT correspondence and understand how to cram infinity into a small circle, and how to knit curved space with knitting needles. And finally, the green disk will install utilities and patches for compatibility so that it's easier to apply the knowledge gained. We'll understand how Fermilab scientists experimentally tested whether we live in a hologram, what the holographic principle is useful for, and what quantum computing has to do with it. Well, I warned you it's going to be powerful. Let's load up and go. Oh, I forgot to say that the blue disk takes a long time to load, so while it's loading, I'll tell you something else. I think it's no secret to anyone that physics is needed not only for physics because it helps solve many applied problems, whether it's designing buildings, developing games, pharmaceuticals, mining, the list goes on. All these are interdisciplinary areas where you need to be well-versed in very different fields. It's difficult, but it yields amazing results. And now I'm in an accredited university that trains specialists to work in such interdisciplinary areas. This approach to education is denoted by the acronym STEM, and the university itself is called Central University. There are bachelor's and master's programs in various fields. artificial intelligence development, business and analytics, joint programs with HSC and MIPT. The education is flexible. Students have the opportunity to choose a program after the first year and tailor the educational process to themselves, leaving only the necessary courses. But most importantly, students receive not only fundamental knowledge but also hone it in practice by solving real business problems. And also, the rector here, Evgeny Vashkevich, is an MIPT graduate, and the head of STEM bachelor's training, Pavel Ski, is a MSU physics faculty graduate. They know exactly where and when physics can come in handy. At Central University, we use the so-called STEM approach to education, which includes mathematics, technology, and all natural science disciplines, including physics. The approach also implies that students focus on problems, work in teams, and use an interdisciplinary approach, where some subjects influence others, and knowledge from one subject is used in the educational process of another subject. Why is this important? Because at Central University, we have more than 5 partners from various fields, including IT companies, engineering companies, companies involved in biology and chemistry. And it's very important for a student to be well-versed in the spectrum of these companies, what they do, and make their future choice, their future profession, reasonably and consciously. In their second year, Central University students have the opportunity to study within the STEM course, where they encounter real sector tasks offered by partner companies. This is how we develop critical and abstract thinking. This is the kind of professionals we train at Central University. And regarding admissions, the university is currently running a grant competition for the bachelor's program, in which you can cover up to 100% of the tuition fees. To participate, you need to register and pass the selection process. So dive into the link in the description and apply for a grant to enroll in a modern, strong university with great prospects. Good luck. Well, now everything is definitely ready. Let's go. So welcome to the first stage of reprogramming your thinking, and to begin with, let's understand how ordinary holograms work. Let me remind you, these are glass plates on which a three-dimensional image is recorded. You can even make them yourself, and right now we don't need to delve into the details of how they work. The main thing is to understand and realize the principle itself, why they are possible at all. The fact is that the picture on the plate is in a very thin layer, you could say zero thickness. So the recording is indeed two-dimensional, but it contains information about 3 dimensions. How is such magic possible? Look, a hologram is recorded using 2 laser beams. One hits the plate reflected from objects, and if it were the only one, only the intensity of light would be recorded, resulting in an analog of an ordinary flat photograph. The second beam falls on the plate directly. It cleverly mixes with the first, which is called interference, and it is thanks to it that information about the distance traveled by light is added to the plate, from which you can reconstruct the volume, the third dimension. It seems already clear. But the information about the distance is recorded in the same place, in the same layer as the information about the intensity, and it doesn't interfere with it, it doesn't erase it. It's the same as if we took 2 independent pictures, somehow combined them, somehow glued them together, but we still have the ability to separate them back. I think the hardest thing is to realize this, so let's consider an auxiliary example. Suppose we have 2 matrices of natural numbers. In essence, these could be 2 digital pictures. How to get one matrix of the same dimension from them and then reconstruct the 2 original ones back from it? There are many options. The most obvious is to write the numbers in different digits like this. We get one matrix. Each element has become larger, but they are still natural numbers, and reconstruction won't be difficult. We take numbers from different digits and it's done. It all worked out because 2 conditions were met. There were no restrictions on the size of the elements, and we introduced rules for combining and separating the matrices. The same goes for ordinary holograms. They can only be recorded on emulsions with very high resolution, so we are not limited in the size of the picture elements, and there is a rule of combining and separating, which is the law of light propagation, which laser beams, of course, obey unquestioningly. Where else would they go? So you can even consider it this way. In a hologram, coordinates on the plate and the rules of propagation and addition of light waves are used to record a 3-dimensional picture. In total, you get the same 3 parameters, and it doesn't sound so paradoxical anymore. although it's still amazing that such a life hack with saving a whole dimension would be useful when packing a suitcase. But how did physicists come to the conclusion that the universe is a hologram? The theory of everything is the result of the search for a theory of everything that can describe all phenomena in nature. It doesn't exist yet, and its appearance requires at least the unification of two global theories: the theory of relativity, which describes gravity, and quantum theory, which describes all other interactions. And frankly, at almost all scales, this has already been done. They combine perfectly and don't conflict anywhere, except in cases where the distance becomes 100 billion times smaller than the size of a proton, and at energies 10 billion times greater than those achieved at the Large Hadron Collider, which are called the Planck length and Planck energy, respectively. Then problems begin. Gravitational effects become so strong that they contradict quantum laws. To be precise, any attempts to quantize gravity lead to the emergence of irremovable infinities and complete fiasco. So, theoretical physicists have been searching for an approach to combine such different theories for 60–70 years. In the 70s, string theory appeared, describing particles not as points, but as objects with a certain length, which are called strings. The particles of gravity correspond to the ground state of the string. So gravity arises in the most natural way. In the 80s, loop quantum gravity was developed, in which both space and time are not continuous but consist of tiny bricks which are mathematically described by loops, hence the name. But these are all theories that we still cannot verify. And in the 90s, another extremely unusual approach to describing the universe appeared with a bunch of inconsistencies. The holographic principle by Gerard Hooft, in which he laid the fundamental principle: whatever the theory of quantum gravity, all processes described by it in the volume of some limited space can be considered a recording on the boundary of that space. And this is an area where the dimension is one less. This is the holographic principle. To describe everything that happens, figuratively speaking, in the volume of a room, we only need the surface of its walls. In 1995, Leonard Susskind continued these ideas. He published an article with the immodest title "The World as a Hologram," where he claims that the entire universe can be considered a recording on some surface, and proposes using string theory for quantum gravity. And just think about what they proposed for a moment on a global level. Firstly, this is a big step towards creating a theory of everything. The principle they found opened up a huge space for creativity for theoretical physicists. Secondly, the holographic principle allowed us to rethink the nature of black holes, but more on that later. And third, my favorite: if the descriptions in the volume and on the boundary are equivalent, then maybe there is no volume at all and we are all two-dimensional flat beings. The truth is only two dimensions, and the third is some kind of illusion. It is not fundamental, but appears on a microscopic level due to some deep laws of nature that we have not yet discovered. It's somewhat similar to a book with 3D pictures. To simplify, it's flat, but its structure has embedded patterns that allow us to complete another spatial dimension. And who knows, maybe that's how everything is arranged on a microscopic level. It's called emergence. It's like the color of a wall. The individual atoms that make it up are colorless, but in the end they combine into an object that reflects strictly defined wavelengths, or like temperature and pressure. An individual molecule doesn't have them in principle. These physical quantities arise only when there are many molecules, or gravity. We perceive it as a force, although according to the theory of relativity, it's not a force but a consequence of the curvature of spacetime. It may even turn out that time is just an illusion. Just imagine, all our perception of causality and the sequence of events is a macroscopic phenomenon, not a fundamental characteristic of the universe. And not only does this mean that all your lateness and time mistakes are literally recorded in the fabric of space-time, it also requires a revision of the concepts of the beginning and end of the universe. All this is very interesting, but nothing is clear. After all, how exactly does it work? How does this dimension appear? How does it collapse? What theory describes it? In those two articles, there are no strict mathematical proofs and clear patterns, at most formulas like in a 9th grade math textbook. Only the principle itself and the general approach are given, but the wait is not long. In 1997, an article was published that found a strict mathematical embodiment of the holographic principle, how it can actually work. Everything turned out to be more complicated than we would have liked, but it's okay, we've already prepared our gray matter so we can handle it at the next stage. We take our red disk. Now the process of installing a new consciousness will begin. It's the most time-consuming, but there's no other way. Well, actually, don't be afraid, it will be a bit hardcore, but we'll manage. So in 1997, an article by Juan Maldacena was published, which describes the supposed correspondence of quantum gravity in anti-de Sitter space, ADS, with a conformal field theory, CFT, and I will use this transcription because that's how I want to and because it's the most common in scientific circles. Of course, nothing is clear at all, so let's go in order and analyze each component of this complex physical puzzle in detail. So first, ADS spacetime. Anti-de Sitter spacetime, its main feature is negative curvature, which is why many laws work differently there than we are used to. Negative curvature is easy to imagine in a simplified two-dimensional version. It is possessed by the so-called hyperbolic space, which is often depicted as a saddle. It looks cool, but in fact it's a simplified representation because such curvature should be at every point in space, and you should feel exactly in the center of such a saddle everywhere. So more accurately, hyperbolic space looks different, not like chips laid out on a table, but like a surface with a very large number of folds. Due to the negative curvature, the further you go, the more figuratively speaking it becomes. And interestingly, such a construction is easier not to describe or draw, but to knit. Yes, directly with knitting needles. Such an approach was invented by the mathematician Dana Taimina. With each row, you make more stitches, and the surface itself acquires negative curvature. This is exactly the kind of stuff that Lobachevsky's geometry describes. The visualization is beautiful but not very convenient, so we will use another representation, a little simpler. Hyperbolic space is demonstrated by the Poincare model in which the scale decreases with each step, that is, the distances increase, thanks to which an infinite two-dimensional space can be fitted into a circle of finite size. Straight lines in this representation will turn out to be arcs perpendicular to the boundary. So hyperbolic space is infinite to the right anywhere, but you can never reach the boundary. There is even a game where you explore hyperbolic space. I recommend trying it. By the way, the unusualness and paradoxicality of hyperbolic space attract not only physicists and mathematicians. The Dutch artist M.C. Escher loved strange geometric constructions and even created a series of paintings called Circle Limit. There are ones with fish, lizards, angels, and demons. This is the Poincare model in such a beautiful form. Anti-de Sitter spacetime is almost the same, only one more time coordinate is added. It is usually depicted as a cylinder, but you need to understand that time is also curved. Near the boundary it can accelerate, and in the center it can slow down. From the point of view of an external observer, because of this, for example, any object that you throw to the side will return like a boomerang. Light from it and time can even be looped, that is, closed in a ring. In general, there are enough oddities here. But for us, the most important thing is that infinite anti-de Sitter space has a boundary. Surprisingly, the second component, conformal field theory, is also an unusual character, because usually field theories describe the behavior of particles and quasi-particles, but not this one. Conformal means that the theory is simplified according to the following principle. It remains unchanged when the scale changes. That is, no matter how much you zoom in or out, it will always be the same, like an infinite fractal. And since that's the case, there can be no characteristic sizes, energies, charges, masses of particles in such a theory. Yes, even the particles themselves in the usual sense. Instead, there are conditional wave packets and states without a clear boundary and scales. To make it even clearer, I will compare conformal field theory with something more familiar, the standard model and quantum field theory. These are also something about particles, about fields, about quanta. Here's the difference. Look, quantum field theory is a powerful tool for describing particles. You could say notes, a recipe, a set of techniques for filming a movie. The standard model is a specific realization of quantum field theory, describing real particles. You could say a finished building, a formal symphony, a finished dish, or a blockbuster from a Hollywood studio. Then conformal field theory is an architectural concept, jazz jam, molecular cuisine, or even art house. In general, a very beautiful, strict, regular, but such a thing in itself, not very practical. And finally, the third component, correspondence. If anti-de Sitter space describes gravity, then on the boundary, you can assemble such a conformal field theory that every physical entity in the volume will necessarily correspond to something on the boundary. There will be some kind of twin. For example, the radial coordinate in the volume is the scale of the conformal theory. The graviton, the particle of gravity, is the energy correlations on the boundary, some kind of mutual tension between different points. A black hole in ADS corresponds to a certain thermal state of the fields on the boundary, and an analog of mass in the volume is the rate of decay of correlation functions on the boundary. In general, a physical entity in the volume is a geometric or gravitational object, and on the boundary its operators, currents, correlations, and other quantum objects. Yes, the correspondences are very strange, incomprehensible, and maybe I shouldn't have even voiced them. But never mind, the main thing is that they exist. Therefore, everything that happens in the volume can be described by some processes on the boundary. This is the embodiment of the holographic principle, and in this case the correspondence is mathematically rigorous. But how can this help us? Well, apart from jokes about flat earthers being right, it turns out that conformal field theory without gravity on the boundary is much simpler than complex and confusing quantum gravity in the volume. So this is a great help for creating a theory of everything. Well, that's great, isn't it? Well, I think you've already started to suspect that something's wrong here. It's too far-fetched for a theory that claims to describe the entire universe. Yes, indeed, this is where the portion of enthusiasm ends and the problems begin. It turns out that AD-SCFT correspondence is completely incompatible with the real world. Firstly, the space of our universe is completely different. It's more like de Sitter space with positive curvature, which manifests itself in the accelerating expansion of the universe. Such a space has no boundary, so it's completely unclear on what surface we can be recorded. Secondly, for the correspondence to work, string theory must have supersymmetry, curled up on a microscopic level. We cannot experimentally verify this stuff yet. Thirdly, if on the boundary the conformal theory has no characteristic scales and is more like a fractal, then the same will be true in the volume. And we won't be able to set the usual masses, charges of particles, and other characteristics there, but we can at most describe some fields, all sorts of their curvatures. Well, for example, black holes. And that's it. Fourthly, AD-SCFT correspondence was conceived only to simplify the description of one fundamental interaction, gravity, but there are also electromagnetism, strong and weak interactions, and it copes much worse with them. Fifthly, even if AD-SCFT correspondence could be used to give some predictions for real objects, they would be extreme energies, temperatures, sizes, which also excludes experimental verification. Alas. Okay, that's enough. Maybe we have proven that the universe is a hologram, but not our universe, but some strange curve without particles. And then the question arises, what are we doing at all, and what have we been discussing for these 20 minutes with only bewilderment? Calm down, don't disperse. Firstly, the holography of our world may arise in some other way that we have not yet discovered. I just couldn't help but mention AD-SCFT correspondence. It's too interesting and important for physics. And secondly, that's not all. There's the green disk. We still need to install more utilitarian and practical knowledge. And then this whole story with the holographic principle will take a new turn and shine with different colors. It turns out that it's still possible to experimentally test whether we live in a hologram, and the principle itself has changed physics and is used in the most advanced areas of science. In general, you'll see for yourselves now. Well, that's enough theory. Let's move on to practice. On one hand, it sounds simple to conduct an experiment and determine whether the world is a hologram or not, but on the other hand, how do we do it? We have no idea how everything is arranged. Moreover, if a 2D equivalent is 3D, then how do we understand the difference and determine what is true and what is false? Surprisingly, scientists from Fermilab found a way and conducted an experiment in 2014. The idea is simply crazy, pure scientific rock and roll. Look, as I said, the theory of relativity and quantum physics are incompatible at the Planck length scale. So in a hypothetical theory of everything, structures of spacetime arise precisely at this mark. They are often compared to pixels. In general, there may be something even smaller, we don't know, but at least at the Planck length level, theories predict a certain stepwise discreteness of spacetime. Alas, we cannot see this graininess because the most accurate devices at the moment, atomic interferometers, are capable of measuring quantities only 100,000 billion times larger than the Planck length. But another thing is important for us. In that case, the recording itself on the surface of the hologram, if it exists, must be discrete cellular, and the boundaries of these cells are not stationary. They experience quantum fluctuations. So when restoring the volume, a certain noise arises, certain microscopic distortions in the sizes of objects. This is called holographic noise, and it can be detected. Two facts contribute to this. Firstly, since information from two dimensions is smeared into three, the size of fluctuations becomes larger, so large that they can be measured. It's like the shadow of an object, which can be larger than the object itself. It's approximately the same here. And secondly, each point in space is built not from its specific section of the hologram, but from its entire surface. So at 2 points the noise will not be absolutely independent, since it has essentially one source. It will be correlated, unlike any other noise which is different at different points. So it can be unambiguously determined and proven that we live in a hologram. Cool, right? That's exactly what they tried to do in 2014. They built two interferometers with an arm length of 39 meters and began searching for microscopic correlated fluctuations. After a year of work, they published the results, and then the whole world learned that the scientists found nothing in the data. There was no hint of holographic noise, so the sensation was cancelled. That's bad. Well, a negative result is also a result. It doesn't cancel the holography of the universe. It just imposes large restrictions on how it can be arranged. Either the noise itself or some of our assumptions are incorrect. We will continue to search, especially since gravitational wave detectors can be converted to search for holographic noise. But the most interesting thing is that even without this, scientists have found many areas where the holographic approach has proven useful. For example, for a deeper study of black holes. The so-called no-hair theorem of black holes is known, according to which any details of objects falling into it do not affect the external parameters of the black hole. Only three quantities change: mass, charge, and angular momentum. And for example, a black hole made of matter will not differ in any way from a black hole made of antimatter, which is why they are called bald without any details. Such behavior contradicts quantum laws, according to which no information can disappear without a trace. You can try as hard as you like, but somewhere there must be data by which you can restore everything that fell into the black hole. This is called the information paradox of black holes, and the holographic principle allows it to be resolved. By the way, in the first iteration, it was developed precisely for this. It is believed that everything that happens inside a black hole can be recorded on its boundary, near the event horizon, at least in some fluctuations of the gravitational field. For an outside observer, this is even visually so, because due to extreme gravity, it will seem to him that the object is approaching the horizon infinitely long and remains next to it forever. In the future, information will leave the universe through Hawking radiation, but the main thing is that it remains in some form and does not disappear without a trace. Well, with the help of add-SCFT correspondence, although it is not possible to directly describe all these processes, you can look for new approaches for a quantum description of black holes. But this is not all. Add-SCFT correspondence can be used as a dictionary, a translator, a book with notes in two languages at once. And if we have, for example, a complex problem in gravity, we can simplify it by translating it into a quantum language, or we can do the opposite. For example, this is how they proceed when studying strongly interacting systems. For example, quark-gluon plasma, which filled the universe in the first moment, or high-temperature superconductors, which can change everything in energy, transport, and everything related to any electrical engineering. All this is related to the description of a large number of particles. Calculations are carried out in two stages. First, they neglect small parameters, for example, elements that make a small contribution to the evolution of the system. They solve the simplified problem and then return the unaccounted elements back as some perturbations. This slightly changes the intermediate result, and the final answer is obtained. This is called perturbation theory. In strongly interacting systems, this will not work because nothing can be neglected. This is where add-SCFT correspondence comes to the rescue. It turns out that if on the boundary a complex, strongly interacting quantum system is described, it will be equivalent to a simpler, weakly interacting gravitational model in the volume. It turns out that this is the holographic principle in reverse. This approach is already used, for example, at the Large Hadron Collider for modeling heavy ion collisions or for superconductors. It allows calculating the density of states, critical temperatures, and modeling the behavior of conductivity. The holographic principle is also useful for quantum computing. For example, it inspired the development of so-called tensor networks, in which the state of the system is described by a smaller number of variables, which simplifies the calculation. Plus, in quantum computing, it is important that information is resistant to noise, to decoherence, and the holographic principle shows how it can be distributed throughout the system, similar to how information is encoded on the boundary of add-S space, which makes it more noise-resistant. With the help of add-SCFT correspondence, the masses of mesons and baryons are calculated. It is useful for studying density fluctuations in the early universe and the formation of its large-scale structure. It is used to describe quantum phase transitions near absolute zero. I haven't even mentioned that add-SCFT correspondence is a powerful tool in theoretical physics for finding new approaches and principles. It's a sandbox in which it's convenient to experiment and develop new physics. So as you can see, it turned out to be not at all useless, and who knows where it will lead. Maybe the creation of a teleport and a photon engine is not far off. That's how things are. Well, how did you like it? I hope you're not too tired and not disappointed. I myself thought that the holographic principle was something about a flat universe, about the illusoriness of reality, but it turned out that this is too bold an assumption. In practice, it is useful in something completely different, but I really enjoyed it.